Recording is rolling. So it's Wednesday, May 11th. So you guys have out your quantum mechanics journals. You guys remember these, all the list of topics we're covering. We did the first few yesterday, got to start. Okay. Today we should get through number 12. That's my goal. That's for last class. Okay, now, before we get rolling too deep into this, back up and remind you guys something, because I know we're getting real close to the end of the semester, or end of the year, end of the school year. So let's take a look real fast. Final exams, for most of you guys, your first one is on Monday the 23rd, but for seniors, your first one is tomorrow, and that happens to be fourth period. Since this class is fourth period, I know we've got, I think, 4 seniors in here. So if you're a senior, then tomorrow I will give you a grade that looks like this, number 1 through 100. Okay? And I've got the final exam printed out. I'll either send you out to the hall or back into the lab area if you have a favorite between those two, and just have you guys take the final exam. So I know since seniors are going to be taking the exam, and we're going to use class time for that. If you miss some of the quantum journal tomorrow, specifically while you're taking the exam, then that's all right. I won't have you make up that part. So anything that like seniors have to miss because either they've taken an exam or graduated, won't hold you accountable for that. Okay, but anything in class today, just follow along with us. You guys know it's I told you guys open notes, study guide, whenever the whole thing with you guys, everything's on Google Classroom. So yeah, as long as you're ready for that. All right. So this quantum mechanics journal. Remember quantum mechanics, we're looking at what's the physics of really small things, so like atom size or even smaller, subatomic particles. Right? Think about how crazy small that is. Now, historically, chronologically, some of the first evidence that something was amiss with classical mechanics was this photoelectric effect. So just over 100 years ago, which showed that it was, say if you shine a light on a PV cell and you're capturing any energy. Well, if you make it more intense, like make it brighter, classically you should expect to get energy that way. But that's not what the experiment shows. The experiment shows that actually increasing frequency is like more energy captured, and it's a direct relationship. Right. So Einstein was able to explain this photoelectric event by saying that light actually has particle-like properties. Right? Since we were talking about Planck's constant, we were looking at Planck time and Planck length, so it's sort of a quantization of space-time. All right, and that's how far we got. And so let's pick up here at de Broglie wave-particle duality. So do what I did yesterday. Gonna switch back and forth. Gonna play a couple of videos for you guys. Show a couple of slides, right, and then go back and fill in some details. De Broglie wavelength.
Photoelectric effect not only confirmed Planck's theory, it showed directly that bundles of energy already exist in the electromagnetic field. In other words, light comes in particles which are now called photons. But wait a minute. A century earlier, Thomas Young had proved light travels in waves. Was it now going to turn out that light is really made of particles after all? Perhaps this whole business of particles and waves was in need of an entirely fresh perspective. Louis de Broglie got a history degree en route to a career in French government, a fresh approach to physics if there ever was one. Maybe that's why in the 1920s, he was the one to ask a crucial question. If light waves can be particles, is it possible that particles such as electrons can also be waves? To begin with, particles have energy and momentum, while waves have frequency and wavelength. Obviously, these entities have different kinds of properties. But de Broglie suspected there was some sort of connection. And Planck's theory had given a clue to what it might be. Max Planck had associated the energy of a light particle with the frequency of its wave. Going a step further, De Broglie combined this with the particle's energy according to Einstein's relativity theory. E equals mc squared. This bold mixture of wave and particle properties suggested the next step. Could particles traveling at less than the speed of light have their momentum related to their wavelength? De Broglie believed so. He thought that just as a particle's energy is related to a frequency, a particle's momentum is related to a wavelength.
All right. So interesting idea. And then experiments have since borne this out. In the next ones we're going to look at are examples of this. Right, so, but this is a bridge between what we did yesterday and the next few that we're about to go into. Right. So particles have certain properties, right? Like mass, velocity, momentum, all that, right? And then waves will have a frequency and a wavelength. So classical physics is thought as like two categories of things, right? But now, starting with the photoelectric effect yesterday, we see well this sort of like mixing, like photons have both wave properties and now particle properties too. So De Broglie is wondering, can I expand this like for like do all particles have like some wavelength? Right, so he did this math and got this what we call de Broglie wavelength. You guys remember Greek letter lambda we've been using for a wavelength last few months? Okay. It's equal to now from yesterday Planck's constant, which you guys remember is very tiny constant. It's like 10 to the negative 34 right, joule seconds. You guys remember from yesterday? There we go. Right, this number. Divided by the momentum of a particle, right, mass times velocity, and you can actually calculate the wavelength of any particular particle. I remember even back when I was in college taking physics, there was a question thrown at us like, what is the associated wavelength of a baseball thrown at some speed? So you say, okay, I'm going to take Planck's constant, crazy tiny number, divide by the mass times velocity of the baseball, right? And you could actually calculate what the associated wavelength would be. Now it was a crazy tiny number that I don't know if you could like measure that or have any significance, but it would be calculatable. Now, funny thing is though, if the mass of the particle is small enough, think like electron, like a subatomic particle, like an electron, then the wavelength actually becomes large enough to be significant and actually drive the properties of say what an electron will do, which is going to lead to this this next one, energy levels and electron waves. So when you guys took chemistry, I'm setting up the next one while you guys are finishing this one up. Right? When you guys take chemistry, do you guys remember the periodic tables are arranged a certain way? There's certain periodic patterns. Electrons will fill certain orbitals. Electrons go something like 2, 8, 18, 32, right? Electrons in a shell. And there's certain chemical reactions that happen because electrons occupy certain orbitals. But now the question to go over to physics, right? Quantum physics is why? Why do electrons only occupy certain energy levels? And that has to do with the fact that electrons have a significant wavelength. So let's kick over back to this screen. And you know what? Actually, let's do this. Just going to show you guys a couple of slides and yeah, so we'll just do a couple slides. Okay, so here's here's the suborbitals that electrons will fill up. They fill it in a certain order. Right, so the order is going to go. Where is it? Here you go. This one right here. Does this look familiar, possibly from electron configuration, like from chemistry? Okay, I'm going to jot that down because I think it's kind of interesting. Yeah, no, this comes from a chemistry textbook. Right? You guys probably saw this last year. Copy a little bit of it, maybe not the whole thing. I will copy down to like 4s. That covers a lot of atoms. Okay. And those arrows tell you the order that the orbitals will fill up. Okay. So 1s covers both hydrogen and helium, and then to get to the third element, lithium, you have to go down to the next level, so the 2s. Right? And each of those can hold like 2 electrons, and then it'll go on there. Okay, so flip the screen back. Right. Didn't copy the whole thing, just part of it. So electrons fill these first. There's hydrogen, helium. Here's lithium, and what is element number 4? Is it beryllium? I think. Okay, right. And then I think it goes boron. Okay, and carbon, and then gone from there. Okay. Okay, so why is this? Well, actually, you guys have seen the model for this. Oh, here it is. I have it right here. Right in arm's reach. You guys remember covering the final exam review? There were a few quantum mechanics questions, and one of them was this right here. Why do electrons occupy only certain orbitals? Well, it's because an electron will have an associated wavelength, and there have to be a whole number of wavelengths to complete an orbital. Okay? So I'm going to draw this right here. So here's my nucleus, protons and neutrons. Right now I've got an electron going around. We try to draw it with like 5 wavelengths. That's pretty close, right? Like 5 wavelengths. Okay? But it couldn't have like 5.5 or 4.5 or 4.75. It has to be a whole number. You're kind of like having some number of paper clips. Right? You can have like 4 paper clips or 5 paper clips or 6 paper clips. Oh, and that means that there will be like certain orbitals that are set up. So the fact that here, label this electron. This electron has certain wave properties. Okay. So you guys got that for number 6. Everybody follow along? That's good. Okay. Oh, you guys are wrapping that one up. Just in case anybody at this point like still doesn't, I don't know, have paper or list of topics or something, I'll put it all right here for you guys. Better late than never if you have to start, because all these are going on Google Classroom. I'll pick this up at the end of the whole deal. All right, and this is going to lead to actually an interesting specific example. This is like, why is glass transparent? So think about like all the materials in this room. Now, why can't we see the classrooms around us? Well, because the walls are not transparent. They're where we can see next door. They're made out of glass or something. Or look at that glass window, though. You can definitely see that glass window. Okay, why can we see through that glass window? Why can't we see like through the air or through water or distance? What makes something transparent? And there is a quantum mechanical explanation for this. So kick back over to screen 2. All right, let's go 60 symbols.
What makes glass transparent? Why can light get through this? Yeah, I've found a number of interesting and disturbing websites, I guess wrong answers, disturbingly wrong, in that they explain it in terms of, well, glass is like a liquid and the molecules don't pack as tightly as they do in a solid, and therefore there are gaps in glass that the light can get through. That is wrong. Badly wrong on so many different levels. Yeah, so what is going on is it's with glass compared to other materials, the important thing is how the atoms are arranged in the solid. And how the atoms are arranged dictates, and this is the really important bit, how the electrons are arranged. And it's how those electrons stack up in different energy levels, or the energies of those electrons, that dictates whether light can get through. Right, so what I'm going to do now is I'm going to pretend to be a photon. I'm going to move through this room, and this room represents a substance, lots of atoms, electrons dotted around everywhere. So I'm moving through with a certain amount of energy. And my job as a photon is actually to take one of these electrons from its ground state, its lowest energy state, move it up and bring it up to a higher energy level. And when I do that, basically my job is done and I'm absorbed and I don't make it through the solid. So if it's brick, for example, this is what happens. The photon comes through, it takes an electron from the ground state, moves it to a higher energy level, is absorbed, doesn't make it through. The substance is opaque. For glass and other special materials which are transparent, instead of what happens is that the difference in energy between the ground state and the high energy level, which we call the energy gap, is much too large. And as a photon, I'm coming through, and what I need to do, or to be absorbed, what I need to do is actually take one of these electrons and bring it all the way up here to this excited energy level. But I don't have enough energy to do that. I simply can't get it up there. So therefore, I'm not absorbed, and I pass through the material.
Mr. It's sort of a counterexample. I'll give you guys a little bit bigger context. So just Google this real fast, infrared imaging. Right. So if you take pictures in infrared and then convert those wavelengths over to like visible light, oh, hey, it looks like this, right? So when you say something is transparent, it's only transparent in certain parts of the electromagnetic spectrum. So like infrared can pass through some materials but not others. Visible light can pass through certain materials and not others. Ultraviolet, same story. Right? So I'll give you guys a little bit broader context right there. Let's kick back over to the screen right here. Show you guys what I got out of that. All right, so looking at these electron waves, right? Suppose you have like an orbital here, right? Expand that here and here. Here's an electron. Here's an electron. Right? You guys see these electrons going around? Okay. And if there's, say, a ray of light with some associated wavelength and frequency, right? Has some photons, right? If that's not enough energy to kick this electron from this state, this orbital to this orbital, that means that there's going to be no energy transfer. Therefore, the photon can just pass through. That's what will make it transparent. Okay? Versus opaque materials like this wall or this border here, you can't see next door. Okay? Those, anytime a light hits it, it's going to kick these electrons up. Therefore, the photon is absorbed and the light does not pass through. Okay? And you can't see it on the other side of the wall, at least not in the visible spectrum. Now, if you go to like ultraviolet or infrared, maybe a different story. Maybe we could peek next door and see what they're doing next door. Okay? Not in the visible spectrum, though, right? Okay. So this energy gap is too large to absorb the photons, so the photons pass through, transparent. All right, guys go there. Okay, while you guys are wrapping that up, introduce this next one, wave function and Schrodinger's equation. All right, so remember before we ever started on this packet, I threw you guys some statistics puzzles, right? We went over those for a few days, right? And one of the reasons I do it, I want you guys to have a model in your mind of what probability curves look like, right? Because that'll help you think about this next one. When you get down to the quantum level, particles don't really exist in as discrete points. They more exist in like waves of probabilities. So let's take a look at Schrodinger's equation. Now, it should tell you guys this math is beyond any math I ever took in college, you think, so can't exactly explain it. I mean, that's true for a lot of these topics. There's a lot of these topics I'm explaining. I know like teachers stand in the front of the room trying to explain the stuff best I can. I don't 100% understand like a lot of the stuff or be able to like personally verify a lot of the stuff. I'm just like saying my research up here, but here we go. Here's what Schrodinger's equation looks like. So we've got a time dependent and time independent versions, but I can tell you what I'm told this means, and that's that, say if you look at a particular subatomic particle like an electron or a photon, where does it exist? Well, it actually exists in, like there's a probabilistic existence to it, right? So let me roll a video. This guy explains a little bit better I can.
All right, so let's talk about quantum physics. What is quantum physics? Quantum physics is what happens to physics when we give wave properties to matter. So matter no longer is allowed to sit in just one place, like object sitting there. We've got to have it spread out like a wave. And that's why we call it given wave properties to matter. All right, so it's described by something called a wave function. All right, and so that's going to take the place of a position, a momentum, and all those things. Instead of that, we describe the behavior of a particle by its wave function. The wave function satisfies something called Schrodinger's equation, which kind of takes the place of conservation of energy. You can think of it that way in quantum mechanics. All right, so if we leave the particle alone, it behaves like a wave. So we're just sitting there, letting the system do whatever it wants to do, and it's described by its wave function. However, if we perform a measurement, suddenly we get something called the collapse of the wave function. So for example, if we've got a wave function that looks like that, and then we perform a measurement and we say, is the particle between these two green lines? Well, I mean, we're performing a measurement. It either is or it isn't. So it doesn't get to say, oh, part of me's there and part of, no, it doesn't get to say that. We're performing a measurement. We're asking, is it or is it not? It cannot be both. And that is going to give us a probabilistic interpretation from quantum mechanics. So the wave function will give us probabilities. It'll say, all right, if you did that measurement 100 times, 6 times you're going to find that it was between the green bars, and the other 94 times you're going to find that it wasn't.
All right, so back over here, I've got a slightly different version of this because I've seen an animation of this play out in 3D. So I'll give you guys a 2D cross section of that on this paper, this wave function. So remember how these electrons could exist in specific orbitals? So let's say we're looking at an electron. Where's the electron, right? Right. So and you perform like 1,000 measurements. Well, you'll see it kind of scattered all over the place. You can make a probability curve that might look something kind of like this, and that would be described by the Schrodinger equation. Okay? So the location of matter is going to exist probabilistically, okay, according to wave function. Okay? Until you make a measurement, and once you make, so got probability versus location graph, right? Now, once you make a measurement, then that wave function collapses, and you can figure out like a lot more precisely exactly where the electron is. Let's say you make the measurement, it happens to be like exactly like right here. Okay. So used to be kind of spread out, let's say over this distance, and now we've narrowed it down to a much smaller distance. So more narrow than right. You can never know like exactly down to the like 10 to the negative 100 meter, but okay. Oh yeah. So location of matter exists probabilistically, described by a wave function. We got probability versus location. A measurement collapses the wave function to one reality. Right? There you go. And then, so once you make that measurement, here's this gets really weird. This is sort of introducing the next few topics we're going to look at. An observation, a measurement, actually affects reality in quantum mechanics, which is a really rare concept. Because so far in this class, we've been assuming that nature is doing its thing. We can be a third person outside observer, say watching a Hot Wheels car roll down a ramp or watching a pendulum swing back and forth. But in quantum mechanics, that's not the case. When you are an observer making measurements, you're actually integrating your reality with the reality of, say, like this electron we're trying to measure. So say you make this measurement and bam, it's right here. It's at this particular location, right? Then everything sort of starts over. And then if you like don't watch it for a while, then say the probability curve would like shift over there, right? To having highest probability at that point. Then you make a measurement of crane again. Let's say it pops up over here. Bam, now it is over there. Now probability curve like resets, right? The Schrodinger equation. Okay. But before you make that measurement, best you can do is probability, make like 1,000 measurements, then we create a curve that looks like that. Okay. You guys got that? All right. Yeah, things are now getting much weirder than this topic. So Heisenberg uncertainty principle. I don't know if you guys may have heard of this before, possibly, because so this is the one that says you can't simultaneously know precisely where a particle is and also its velocity. Oh boy. Oh, aha. These buttons are wearing out over here. Now let's look at an experiment this one. Ooh, yeah.
Today, I'm doing an
It's from the channel Veritasium.
experiment that demonstrates Heisenberg's uncertainty principle. So here I have a green laser, and I'm firing it down towards the front of the room through a narrow slit. Now that slit can be adjusted, so it can be made narrower or wider. And the laser spot is projected onto a screen behind it. So what do you think is going to happen to this spot on the screen as I narrow the slit? Well, let's have a look. You see exactly what you'd expect. The spot gets narrower and narrower. The sides are getting cut off by the slit. Makes complete sense. And if you stop there, you would never realize that Heisenberg's uncertainty principle is at work. But if you keep going, something strange happens. As you make the slit even narrower, the spot starts to spread out. Isn't that incredible? You're making the slit narrower, and yet the spot on the wall is getting wider. The narrower you make it, the wider that spot on the wall becomes. To understand this, we have to look at Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is normally written as delta x, delta p is greater than or equal to h on 4 pi. So what does this mean? Well, it's about the position and the momentum of a particle. So x is the position of the particle and p is its momentum. So delta x is the uncertainty in position and delta p is the uncertainty in the momentum. Now, if you multiply those two quantities together, they must always be greater than or equal to h on 4 pi. Now, h is Planck's constant, and that deserves a video all to itself, like this one by 60 symbols. But for our purposes, it's just a very small number. So in our everyday lives, we don't come up against this uncertainty relation because everything is much, much bigger than h. But as we narrowed the slit, we were decreasing delta x for those photons. So we were getting more and more precise about where the photons were passing through that slit. And at a certain point, you come to this limit so that if you narrow this any further, you're going to break this uncertainty relationship. So what needs to happen is the uncertainty and momentum needs to go up. I should specify this is uncertainty and momentum in the x direction, in the horizontal direction. So if before photons were going perfectly straight, now they must veer off to the left or to the right to ensure that we don't break Heisenberg's uncertainty relation.
All right, now let's go back to the experiment version of this because I want to point something out here.
And yet the spot,
Yeah, you guys see like spreading out right there? Somebody knows too about spreading out. That's just a single slit that the light's going through. Do you guys see like there's these bands of light? So there's the central band, right? So like most probabilistically, right? Most of the photons are going to hit that big band in the middle. But I see a band to the right, band to the left. If you look even more to the right and the left, do you guys see a really faint band right there? You could probably attach probabilities to each. So maybe there's like I'm just gonna make up some numbers, maybe 95% chance it ends up in the middle. And then let's say a 3% chance it ends up on one of these bands. And then maybe like a 2% chance it ends up on one of the far like faint bands on the right. So, all right, so the probabilities add up to 100%. All right. So stop share, back over. All right, here we go. So here's some stuff I got. So here's what it means, right? Where this way you can't simultaneously precisely know both position and velocity of a particle, right? Well, I'm saying a particle, but really could be anything, right? But particles, it really matters because this constant is so small, right? That you really need like small masses for this to really be relevant, right? Because you guys remember Planck's constant right here. This is like 10 to the minus 34. So already we're talking about like a crazy small number. So normally but it wouldn't be an issue, right? But yeah, if we're talking about like a photon or an electron, right, then if you take uncertainty of position, right, so that's like the size of the slit that's going through in this experiment, that's delta x, uncertainty of position, multiplied by uncertainty of momentum, that's mass times velocity. So that's why I say velocity here, mass times velocity, right? Okay. Then let's just go, it can't be less than this constant, right? So if you run into that, right, that's why it starts to spread out to get some more uncertainty of momentum to compensate for that less uncertainty of position. Okay. All right, now that was a single slit experiment, right? Let's kick over to double slit experiment. Okay, now this one, well, it's going to have a few parts to it. You guys did see double slit experiment going back a few weeks ago when we were looking at light and diffraction. That sort of. You guys remember? Actually, you know what? I guess I copy that down. Let me see if I can scout this out in this textbook real fast, where you guys saw some diffraction, double slit experiment. Aha, here we go. Okay. You guys remember this from the textbook way back in the day? Right. So if you have, say, two slits on a board and you let the water go through, say these ripples go through, right, they'll create this interference pattern. You guys remember this interference pattern? Let's zoom in a bit here. You guys remember that? Right. And back in the day, we cared about, oh, here we go, yeah, Young's interference experiment. Okay. We cared about this just to mark what's the properties of what makes a wave versus what makes a particle. Okay. So let's go back over to computer. Okay. So that's going to start this off. But then when you get to quantum mechanics version of this, there's actually a really weird addendum to this. So here we go.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. Waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands.
All right, so far it's just laying out the definitions of what is a particle, what is a wave. Okay, so nothing weird yet.
Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one, it goes through just the other. All of these possibilities are in superposition with each other.
All right, so maybe even that's not too weird. I mean, maybe it's weird as of like a week ago, but you guys know, electrons have wave properties that are dominant. Right, so blah, blah, blah. We've talked about that last few seconds. So, okay, so maybe a single electron could interfere with itself. So that can make sense if it's all kind of spread out. Right? But here's the real kicker right here where things get like crazy.
But physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched.
All right, so this opens up all kind of crazy possibilities. I mean, the fact that electrons behave differently depending on whether there's some kind of detection equipment. Now I know in this video it's being represented as a cartoon eyeball, but let me show you something closer to the actual experimental setup, which is this one right here.
All right, you ready to have your minds blown? Oh man, your minds are going to be blown big time.
All right, so this is a long video that you have to think really deeply on. I've watched this like 4 or 5 times just to kind of get the gist of what's going on, but I will summarize this for you. Oh, this, by the way, this is called delayed choice quantum eraser. If you want to look this up yourselves. Oh, there we go, delayed choice quantum eraser. And he says, go watch that video first that I just rolled for you guys. Cartoon Dr. Quantum. Okay. Now, what they got here is a laser and a beam splitter. So the photons are split and sit on two different paths. Right? Okay, he's saying by the time they get to this detector, if you see this interference pattern, that means, okay, that exists as a wave, versus if you see just two solid bands, which would say represent like these two slits, then in that case, these photons are acting more like particles. And you can actually get both results, but it depends on say which way these photons have bounced around, which could give you information a lot like, hey, kind of like that cartoon eyeball. It's instead of a cartoon eyeball, now it's just this whole rig setup. So you can figure out, okay, well, if this one goes this way, you have to go through this whole logic process. But I'm saying this is out there so you can find it and think about it deeply yourselves. But yeah, the consequence of this then is that if you do not observe an electron, then it exists as a wave of potentials. Once you make observations, that wave function collapses. So an observer actually is entangled with the outcome of this experiment. There have been different versions of this done. There's been different variations. You can have a detection equipment set up and like store that data away and nobody looks at it and it still acts like a particle. So just the fact that there is data stored somewhere, even if no conscious observer looks at it, right, it'll still go, the wave function will be collapsed and it'll turn from a wave to a particle. And so here's the two parts of this. Right? So we're shooting through like photons, right? So it could be photons or electrons. So just these fundamental particles, but very, very small mass, right? They can have both wave and particle properties, wave particle duality, de Broglie wave particle duality, right? And normally we'll set up this this interference pattern, which would be say an indication of a wave. But if you know too much information, then that wave collapses to one reality. So that turns into like a particle. All right. So while you guys are wrapping that up, that's gonna kick over to this next one, the measurement problem and Schrodinger's cat as an example of this. Right. Measurement problem is, well, like this very idea right here. Right now, for the first time, go back about 100 years ago, 1920s is when quantum mechanics was like really being developed. People were doing experiments like this one, right? And realized that, ooh, by us taking measurements, we're actually affecting reality. Okay, so that's weird. Right, there, one of these very famous quantum physicists was a guy named Erwin Schrödinger. And this like really bothered him. Of course, this is all groundbreaking physics in the 1920s. And he came up with a thought experiment, I'll call it Schrödinger's cat, to try to sort of like poke holes in this or say there's no way this could be true because, right? And he goes into this story about this cat in the box. You guys ready to see the story about this cat in the box? All right, so flip back over. Cat in the box time. Yeah, all right. And so this particular experiment goes, recap the experiment and take us to implications and interpretations of this. So again, this is just a thought experiment. Nobody has ever actually like put the cat in a box with like cyanide and actually tried this out. This would be a closed box. Right? If I say closed box, I mean, can't see inside, you can't feel, there's no way to detect, you can't hear what's going on inside, right? Right, so it's completely sealed to the outside world. Right? Got this outside observer looking at this box, like, I wonder what's going on in there. Now we've got a radioactive atom. Let's say it has a half-life of like 1 hour. Some radioactive atoms have half-life of like fraction of a second, some are thousands of years. Let's go with like 1 hour. And let's say once it decays, it's going to trip some system that's going to release cyanide gas, and that would kill the cat. Right. So here's this outside observer. He's watching. He puts everything in the box, closes the lid. It's like, okay, well, half-life of 1 hour. That means that after 1 hour has passed, there's a 50-50 chance that this whole process is kicked off and the cat's dead, and a 50-50 chance that it hasn't and the cat's still alive. Right. At least that's how you would think classically. But in quantum mechanics, what you say is, well, the atom exists in a state of superposition until it's observed. Therefore, it's both decayed and not decayed. It's decayed probabilistically. Right. But if that's true, then since the fact that it's tied to the macroscopic world, the cat is both dead, is described in terms of quantum mechanics as being both dead and alive simultaneously, also in a state of superposition until it is observed. Yeah, so this connects the quantum and macroscopic worlds. You guys remember when we were studying theory of relativity? One thing I was telling you guys was this correspondence principle in science, that if you come up with some theory, some crazy new theory of like, oh, this is how this works, and it's going to replace some old theory, that at least the new theory has to be consistent with what the old theory says, has to cover those bases too. Okay, and this is one of the tricky things about quantum mechanics as well, where like something like de Broglie wavelength. Okay, well, that could fit in because still the mass enough. It's like okay, insignificant wavelength. Right? But something like this, like right? Where exactly is the cutoff, or where do you transition from, say, the quantum rules to the macroscopic rules, or something like that? But let's do one more. Do with you guys. Do you guys know Zeno's paradox? Now, Zeno's paradox, just the classical version, goes back ancient Greece, thousands of years ago. There was say like a guy in a race, run towards the finish line. He could never reach the finish line because he has to go halfway and then halfway and then halfway. So we'll never get there. It's kind of silly and never really mentioned it, but that's it, right? But there's a quantum version of this, which actually is kind of relevant. It has to do with this radioactive decay. So let's say you have a graph. I'm going to put time on this axis and probability of decay on this axis. Okay. Now, after one half-life, T1 half, there should be a 50% chance that it's decayed. So I'll do a little bar graph here. Okay. After two half-lives, well, now we're up to 75%. Okay. After three half-lives, well, now we're up to, what would that be? I think 87.5%, I want to say, like that. Okay. After four half-lives, okay, well, now it's getting closer and closer to 100%. So if you wait like 100 half-lives, well, now it's like almost certainly decayed, right? Like maybe 1 in a billion, that's not right. Okay. But there's something weird if you continuously observe it, right? And that's that with continuous observation. Okay, so let's say we're watching an atom and it should say a half-life of 1 hour. So after 1 hour, 50 chances decay. But if we're constantly observing it, right, see like when exactly does it decay? Atom, or I should say the wave function. So the atom will never decay. The wave function continuously collapses to the original state. Ooh. Okay. So that goes hand in hand with the double slit experiment, that if you are observing a particle, that actually affects its reality. All right, so that is the end of class right there. So that will be our pause points.